In the previous example, we began looking at continuous probability distributions, continuous random variables, and in that example, we looked at uniform probability distributions. And the specific example was a utility worker was going to arrive between 10 and 11 a.m., and it was just as likely that the utility worker would arrive, say, 1 to 2 minutes after 10 a.m., as he or she would be to arrive, say, 14 to 15 minutes after 10 a.m. And the truth is that scenario is a bit contrived. If here is 10 a.m. and if here is 11 a.m., so this was x equals 0 and this was x equals 60 in our previous example. Well, the truth is it's probably more likely that maybe the utility worker would maybe be around somewhere here in the middle, maybe around x equals 30 minutes, than he or she would be to be around the 10 or the 11 minutes. In other words, maybe it's more likely, or probably it's more likely, that the utility worker would be, say, around a 10:30 arrival time than a 10 o'clock or an 11 o'clock arrival time. So my point is that the graph would probably not really be uniform in a scenario like that. It would probably have more of a shape, perhaps something like this. Okay? So where we're moving next, and the reason why I discuss this, is we're going to be talking about a normal curve. So a continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram has the shape of a normal curve. Now, what am I talking about with this? Now, previously, when we studied the binomial probability distribution, we studied the shapes of a binomial probability distribution. So here we have the graph of a binomial distribution that has n equals 10 and p equals 0.2. Well, we discovered before that if we increased the number of repetitions of the binomial experiment, then the shape of the distribution would become more and more perfect. So for example, if I have 1,000 trials, the graph looks more like this. If I have 10,000 trials, the graph looks like this. If I have 100,000, it looks like this. And so this shape gets more and more perfect into this perfect bell-shaped distribution. Well, this perfect bell-shaped distribution that we approach has a name. It's called the normal probability distribution. So we're going to look at the normal probability distribution in more detail next. So, back to our definition. A continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram has the shape of a normal curve. So a normal curve is similar to this that I was talking about with the utility worker. Okay? Specifically, a normal curve is going to have this perfect, smooth bell shape. Okay? And so this is a probability density function for a normal probability distribution. Now, this type of a normal curve has some specific properties that we need to follow. So here are some properties of the normal density curve. The normal curve is symmetric about its mean. Because the mean equals the median equals the mode, the normal curve has a single peak and the highest point occurs at mu. So for our normal curve, this maximum point, the highest point on the entire graph, is going to occur above the mean of our distribution. The normal curve has inflection points at mu minus sigma and mu plus sigma. So from mu, if we move to the right one standard deviation, and that would be mu plus sigma, and if we move to the left one standard deviation, so here would be mu minus sigma, okay? Then the inflection point would be right above those locations, okay? Now an inflection point is a point where a graph changes its curvature. So for example, if you look at this section of this graph, this is called concave down. It's curving downward. But then if you look over here, this is called concave up. It's curving upward. So the point where it switches from curving downward to curving upward is an inflection point. So on a normal curve, we have two of those. So we have an inflection point here because we're going from curving up to curving down. And then again, we have this inflection point here. And those inflection points occur exactly one standard deviation from the mean. Now the total area beneath this normal curve has to equal 1 because it's a probability density function. Okay? So by symmetry, then that means that the area to the right of the mean is going to be 1/2, and the area to the left of the mean is going to equal 1/2 as well. So those are on our list of properties. The normal curve has inflection points. The area under the normal curve is 1. The area under the normal curve to the right of mu equals the area under the curve to the left of mu, which equals 1/2. Now, further, as x gets bigger and bigger and bigger, this graph approaches but never touches the horizontal axis. And the same, as x goes to negative infinity, this graph approaches but never touches the horizontal axis. We call that asymptotic in algebra. So this graph gets asymptotic to the horizontal axis, meaning again it gets closer and closer to it, but it never touches. Closer and closer to it and never touches. Okay? So that is property number 6 on our list. So as x increases without bound, in other words, as it gets larger and larger, the graph approaches but never reaches the horizontal axis. As x decreases without bound, gets more and more negative, the graph approaches but never reaches the horizontal axis. And then last but not least, because the normal curve is a perfect bell shape, the empirical rule applies. So that means that approximately 68% of the area under the normal curve is between mu minus sigma and mu plus sigma. About 95% of the area is between mu minus 2 sigma and mu plus 2 sigma, and approximately 99.7% of the area is between mu minus 3 sigma and mu plus 3 sigma. So here we have a normal distribution, okay, that's illustrating the properties that we've discussed. So we've got this perfect bell shape, this perfect normal curve. It's centered at the mean, so the maximum points occurring above the mean. The inflection points are occurring exactly one standard deviation from the mean. The graph is getting asymptotic both in the positive direction and the negative direction. So as x gets bigger in a positive direction, the graph gets closer and closer to the horizontal axis, and the same in the negative direction. The area beneath the normal curve is 1 because this is a probability density function. By symmetry, that means the area to the right of mu is 1/2 and the area to the left of mu is 1/2. And the empirical rule applies, which we can see illustrated here. Now we'll look at examples in the next video.